The first shell struck just above the tracks. The crew inside felt the jolt rattle their bones. Dust filled the interior. Someone yelled, "We're hit!" But the tank held. The second impact was worse. It slammed into the side of the Sherman's turret, sending sparks through the viewing slit. The driver's hands were shaking. The gunner ducked instinctively, thinking the next hit would be the last. Then came the third, direct, loud, blinding, and then silence. No fire, no breach, no death. Inside that Sherman tank, 5 young Americans stared at one another in disbelief. They had just survived 3 direct hits. According to training manuals, that should not have been possible. According to physics, the weld seams should have cracked. According to every engineer who had studied battlefield stress points, that tank should have been a coffin. But it was not. Thousands of miles away, 2 years earlier, in a factory outside Detroit, a young woman wiped the sweat from her brow as she adjusted her helmet and lowered the welding torch once more. Her name was Margaret Reed. She was 24 years old and had never built anything bigger than a chicken coop before the war. Now she was welding armor plate onto Sherman tanks, one burning inch at a time. Her supervisor stood behind her, arms crossed. He watched her bead pattern for a long moment before finally muttering, "That weld's ugly as hell." Margaret did not look up. She just kept going. "Maybe ugly works," she said. No one at the time understood what she meant. Not the supervisor, not the engineers, not even Margaret herself. But years later, in the shattered fields of Normandy, someone would climb out of a tank that should have been destroyed and realize that somehow it had held together, not because it was flawless, but because of the way it had been built. Because of a line of weld that was uneven, imperfect, even ridiculed, and yet unbreakable. This is the story of how one woman's ugly weld line, dismissed and nearly rejected, became a hidden reason why Sherman tanks began surviving impacts they were never designed to withstand. This is not a story about perfection. It is a story about survival. And how sometimes the thing that does not look right turns out to be exactly what we need. In the winter of 1942, Detroit did not sleep. The sun rose and the factories roared. The sun set and they roared louder. It was the sound of steel being shaped into machines of war, the hum of a nation that had transformed overnight from peacetime industry to military production on a scale the world had never seen. One of the crown jewels of this transformation was a massive facility called the Detroit Arsenal Tank Plant. It was not a battlefield, but it might as well have been. Workers operated in shifts around the clock. Chrysler, the car manufacturer, had been ordered by the government to stop building automobiles. Instead, they were told to build tanks. And they did, with staggering speed. The first Sherman tank rolled off the line just 366 days after the attack on Pearl Harbor. By 1943, the plant was producing one new Sherman tank every 38 minutes. This was not just industry, it was defiance. Adolf Hitler believed that the American people were too soft, too disorganized, too dependent on comfort to fight a total war. He had no idea what was coming. American factories would produce over 85,000 tanks during the war. More than 49,000 of those would be Shermans. They were not the most heavily armored. They were not the most powerful. But they were available, reliable, and everywhere. The German army gave them a nickname, Tommy Cookers, because they burned when hit. But they also noticed something else. They just kept coming. And behind every one of those tanks was a welder, thousands of them. Men, yes, but also women. Many were young, with no industrial experience. They had been secretaries, waitresses, housewives. Now they wore leather aprons and held acetylene torches. They worked 10-hour shifts in heat and noise, turning raw steel into the skeletons of armored beasts. Margaret Reed was one of them. She had grown up on a small farm in Ohio. Her father had taught her how to fix fence posts and drive nails. When the war came, she answered the call, took a bus to Michigan, and passed a welding certification after just 3 weeks of training. Her hands were steady. Her welds were strong. But they were not pretty. It did not matter to her. She was not trying to impress anyone. She was trying to do her part. The welders worked in pairs, often without speaking. They communicated in sparks, gestures, and sweat. The job was brutal. The steel plates were thick. The welding arcs were blinding. The protective gear was heavy. And every minute spent slowing down the line meant another minute a tank was not being shipped to the front. So they moved fast. Sometimes too fast. Inspectors would walk down the line with clipboards, checking seams, pointing out flaws. If a weld looked uneven or inconsistent, it would be marked for correction. Sometimes it was ripped out and done over. But every now and then, something strange happened. An ugly weld, the kind that broke every visual rule in the manual, would still pass the strength test. That contradiction lingered in the minds of a few engineers. They did not know it yet, but the answer was hiding in plain sight. It was buried in the sparks, in the heat, and in the hands of someone like Margaret. Because while the enemy was perfecting tanks with thicker armor and bigger guns, the United States was learning something far more dangerous: how to mass-produce resilience. And sometimes, the most reliable strength came from places no one expected to look. By the spring of 1943, the Detroit Arsenal tank plant was working at full throttle. The goal was simple: volume. More tanks, more steel, more speed. Because on the other side of the Atlantic, American boys were dying every day. In North Africa, in Sicily, in the air over occupied France. The generals needed more Shermans, and Washington made sure the factories understood that failure was not an option. Inside the plant, the pressure was relentless. Welders were expected to keep a pace that would exhaust even the most seasoned craftsmen. Every seam had to be finished in minutes, not hours. The welds were supposed to follow the Lincoln Code, a set of specifications drawn up by Lincoln Electric to ensure structural consistency. Straight beads, uniform depth, smooth transitions. In theory, it was simple. In practice, it was chaos. Steel plates were not always cut perfectly. The fit-up was sometimes off by fractions of an inch. Jigs and clamps were overused, and most of the welders, like Margaret Reed, had only months of experience. They were skilled, yes, but fast-tracked through training programs designed more for war deadlines than for perfection. Supervisors walked the floor with notebooks and red pencils. Welds that looked rough were flagged. Some were ground out and reworked entirely. Time was wasted. Tempers flared. One foreman barked at Margaret one afternoon, pointing to her latest pass along a hull seam. "This looks like a drunk raccoon laid it down." Margaret did not argue. She had heard worse. She wiped her forehead and moved to the next section. But something gnawed at the edges of procedure. In the stress testing area, where completed hulls were subjected to pressure and vibration tests, a pattern started to emerge. Some of the ugly welds, the ones that failed visual inspection, were performing better than the textbook examples. At first, the assumption was error. The machines must be miscalibrated. The readings must be off. But again and again, the data pointed in the same direction. Certain uneven welds were holding up under extreme conditions far better than expected. Engineers were confused. One even joked, "Maybe we should let the new hires teach us." But no one laughed for long, because the frontline reports were coming in, and they were alarming. Sherman tanks were being penetrated. Armor seams were cracking under artillery hits. Weld failures were contributing to tank losses. German shells, especially from the feared 75mm guns on the Panzer IV and the dreaded Tiger, were slicing through hulls and turrets like butter. And when they did, it was the weld lines, not the steel itself, that often failed first. The engineers went back to the drawing board. They reviewed reports. They ran simulations. And one junior metallurgist, a man named Frank Levine, noticed something strange. He had flagged a batch of tanks that had exceeded all durability tests. When he checked their production records, he found that several had come from the same welding bay, the same shift, the same welder. It was Margaret Reed. Her welds were inconsistent, wavy, sometimes off-center. But they were absorbing stress in a way the smooth, uniform beads were not. Frank brought it to his supervisor. The older man looked over the photos and raised an eyebrow. "You want me to tell Washington we should make our welds uglier?" Frank did not have an answer. Yet. But the seed was planted. The idea that what looked wrong might actually be right. That function could live beneath the surface of imperfection. Margaret kept working, unaware of the conversations happening upstairs. She was still being told to fix her style, to make her seams look more professional. She tried, but the war did not wait for beauty, and in the crucible of war, speed and strength were enemies. One had to give. What no one realized yet was that Margaret's mistakes were doing something revolutionary. They were bending instead of breaking. And that, in war, could mean the difference between a tank burning or bringing its crew home alive. It began with a sound, not a bang, not an explosion, but a hollow crack, sharp and dry, echoing from the far end of the testing bay. A prototype Sherman hull had just failed its pressure test. A simulated shell impact had shattered the side seam. Inspectors gathered around, muttering, jotting notes. This had become routine. Another failure. Another weld seam torn under stress. Another reminder that the German guns were not forgiving. Frank Levine stood silently in the corner, arms crossed, staring at the broken edge. He was not a senior engineer. Not yet. But he had been watching patterns, collecting data, measuring test results for weeks. He pulled a clipboard from the table and began flipping pages, comparing batch numbers. This hull had been welded by a top-ranked foreman. Neat, symmetrical seams, picture-perfect lines, but it had split like a dried-out branch. 3 days later, another hull was tested. This one had come from Margaret Reed's line. It looked like hell. Her welds were uneven, thick in places, thin in others, with strange ripple patterns along the edge. And yet, it passed. It did not just pass. It exceeded every threshold. No cracks, no leaks, no warping under pressure. The test team ran it again. Then a third time. They increased the vibration stress. Nothing failed. The engineers huddled. They called Frank over. "What's different?" one asked. Frank smiled slightly. "The weld." They brought in metallurgists. They examined the seams under microscopes. And slowly, a picture began to emerge. The irregular shape of Margaret's welds had changed how stress traveled through the joint. Instead of concentrating force along a single line, as uniform welds often did, the uneven contours dispersed energy. Think of it like a river hitting a jagged shoreline. The water breaks, spreads, flows around. It does not destroy. One expert explained it like this: her welds are ugly to the eye, but beautiful to the molecule. Heat gradients in her torch path created micro-variations in the steel's grain structure. In technical terms, she was accidentally creating a naturally resistant stress flow path. In human terms, her imperfections made the tank tougher. The senior engineer, who had once scoffed at her weld photos, now asked for samples. Margaret still did not know. No one had told her yet. She was on the floor, welding hull number 1612, just trying to stay on pace. But in the upstairs office, something changed. Frank Levine gave her weld pattern a name, unofficial, scribbled in pencil, Reed pattern, variant 3. It would later become part of an internal memo sent to multiple U.S. tank plants, quietly, without announcement. Supervisors were instructed to allow controlled bead variability on select hulls. Engineers began adjusting weld training modules, and gradually, without any medals or fanfare, Margaret's method spread. It was not theory anymore. It was results. The tanks that used her welding style were surviving. In battlefield conditions, those few extra seconds of integrity meant a crew could escape. A fire could be contained. An engine could stay running long enough to reverse out of a kill zone. One combat engineer later wrote in his post-war report, "We do not know who made the change. But since the spring of '43, our tanks break differently. And when they break, more of our boys come home." That was the twist no one saw coming. The flaw, the mistake, the imperfection they had tried to eliminate was the one thing keeping American tanks alive, under fire. And behind it all, a welder no one remembered, doing a job no one glorified, was quietly rewriting what it meant to build for war. Sherman versus the Tiger. The morning fog clung low over the hedgerows of Normandy, thick and silent, as if the land itself was holding its breath. It was June 7th, 1944, just one day after the invasion of France had begun. Sherman tank crews were pushing inland from the beaches, weaving through narrow country roads bordered by high dirt walls and ancient trees. Visibility was terrible. Every curve in the road was a potential ambush. Every rustle in the leaves set nerves on edge. One of those tanks was call sign Lucky 6, part of the 4th Armored Division. The crew had only been in combat for 12 hours, but already the commander, Lieutenant Charles Dawson, had seen more than enough. Dead cows in the fields, burned out half-tracks, paratroopers lying face down in the ditches. His tank had been assembled in Detroit 7 months earlier. On the production tag, welded inside the crew hatch, was the number 1612. They would never know that this particular hull had passed through the hands of Margaret Reed. By mid-morning, the column moved into a sunken lane just outside the village of St. Lo. That was when the first shell struck. It hit low, just behind the driver's hatch, and detonated with a metallic roar that shook the entire vehicle. Everyone inside jolted forward, ears ringing. The gunner swore. The loader screamed, "Hit!" But nothing penetrated. The commander peered through the periscope. Black smoke, trees splintering. Then a second shot came, this time hitting the turret directly. The force slammed into the gun mount, knocking the barrel off alignment. Sparks flew inside the fighting compartment. The lights flickered, but the turret did not crack. The hatch stayed shut. Then the third shell came. It was a high-velocity round from a Tiger tank, the most feared machine on the Western Front. It struck the rear side armor with enough force to send dust pouring through the seams. The driver thought the tank had split open. He reached for the fire extinguisher, but there was no fire, no flames. Just silence. For 5 seconds, no one spoke. Then Lieutenant Dawson yelled, "We're still alive! Reverse now! Get us out of here!" The engine coughed, then caught. With a grinding screech, Lucky 6 lurched backward, kicking up dirt and smoke. The Tiger's gun rotated slowly, searching for its next target, but Lucky 6 was already gone, ducking behind a barn wall and disappearing from sight. When the crew finally dismounted hours later, they examined the damage. The side armor was warped. The turret had a dent the size of a dinner plate. The paint was scorched. But the hull? Intact. The weld seams, rough and uneven, had held. Not by luck, not by chance, but by design. Those ugly lines that inspectors had once ridiculed had just saved 5 lives. The after-action report filed by Dawson described it bluntly. 3 direct hits sustained. No penetration, crew unharmed, armor integrity held beyond expected thresholds. In the weeks that followed, similar stories began to emerge from across the front. Shermans that should have been destroyed, surviving. Crews reporting unexplained resilience. Engineers combing through wrecks and noticing something they had not paid attention to before. Subtle irregularities in the weld seams. What had once been considered a flaw was now a signature. Field repair teams began marking tanks that had Reed-style seams. Not officially, there was no manual yet, but among mechanics and veterans, the rumor spread, if you see the ripple pattern, that one's got a fighting chance. By the fall of 1944, the German army had begun deploying more Tigers and Panthers. Their firepower was terrifying. But American tank crews, increasingly, were surviving first strikes, sometimes second, sometimes even third. The Sherman still could not match the Tiger's gun, but it could move faster, turn tighter, and, thanks to welds like Margaret's, it could take punishment longer than before. That changed tactics. Crews became bolder. They began flanking, rushing, attacking in pairs, knowing that if they got hit once, they might still have time to fight back. In war, seconds matter. And those extra seconds were bought not by armor thickness or mechanical genius. A year later, he tried again. This time, she called. They spoke for 42 minutes. Frank told her everything. About the tests, the reports, the tanks that had survived because of her seams. Margaret was quiet for most of the conversation. Then near the end, she said something he never forgot. I just wanted them to hold. That was all. Not glory, not recognition. Just a simple, steady hope that the medal would hold. Frank nominated her for a civilian commendation. The paperwork was lost in agency reshuffling. He tried again, years later, but Margaret declined. I did my job, she said. That's enough. She passed away in 1998. Her obituary made no mention of tanks or welding or anything to do with war. Just a line about being a devoted wife, mother, and worker. But in a small file drawer in her home, beneath family photos and tax returns, there was a single black and white photo. It showed her in welding gear, arms slung around a fellow worker, sparks flying in the background. Someone had written on the back, Shift 17, built for the fight. There are no monuments to Margaret Reed, no streets named after her, no bronze statues in the National Mall. But if you know where to look, at the underside of a Sherman tank hull, tucked beneath flaking paint and rust, you might find a weld line that doesn't quite follow the book. Rough, uneven, defiant, still holding. And if you do, you'll know exactly whose hands shaped it. History does not always remember the hands that build it, but sometimes those hands leave fingerprints too deep to ignore. In the years after World War II, as the factories transitioned back to peacetime production, a quiet revolution was already underway. Engineers and metallurgists studying wartime equipment noticed patterns. Some tanks had simply held up better than others. The causes were complex. Better steel, better logistics, better luck. But among the variables, one detail kept appearing in testing records, repair logs, and salvage reports: weld seam integrity. And within that category, one phrase surfaced again and again: variable bead pattern. It was not called the Reed pattern anymore. The name had faded. But the method survived, in small notations, in diagrams, in the training slides of the next generation of welders. It became part of the unspoken gospel of practical engineering. Under combat stress, imperfect welds, when done with enough penetration and consistency, often performed better than the visually flawless ones. Post-war welding textbooks began including references but by a welder thousands of miles away, who had never heard the sound of artillery, but had felt the heat of the torch every day. Margaret Reed never saw a battlefield, but her welds did, thousands of them, silently holding their shape under fire, saving lives one arc at a time. Lucky 6 would go on to fight in 4 more battles. It was eventually decommissioned in 1945, shipped back to the States, and later placed in a county fairgrounds as a war memorial. The crew scattered. Some went home. One, the loader, never made it past Bastogne. But the tank stayed. And if you look closely, under the flaking green paint, you can still see the seam. A rough, jagged line along the lower hull. Not perfect, not beautiful, but still holding. When the war ended in 1945, the factories did not fall silent all at once. Production slowed, then stopped. Assembly lines were repurposed. Welding torches cooled. And the workers, the men and women who had kept the arsenal of democracy alive, were told it was time to go home. Some returned to farms. Others found jobs in the auto industry. Many of the women, like Margaret Reed, were quietly laid off, their wartime roles deemed temporary. No parades, no farewell speeches, just a final paycheck, a thank you letter, and a closed gate behind them. Margaret took a bus back to Ohio. She moved in with her sister, worked at a hardware store, got married, raised 2 children, and like so many others, she rarely spoke of the war. She had never worn a uniform, never fired a gun. She had no medals, no stories of heroism, just the faint burn scars on her forearms and a drawer full of Union pay stubs stamped with the Chrysler seal. Decades passed. Her name faded from any records. The tanks she helped build were decommissioned, scrapped, or sent to museums. Her weld pattern, once copied and passed quietly among engineers, became absorbed into later manuals, adapted, revised, and eventually attributed to general field variation allowances. No one remembered the woman behind it. No one, except one man. Frank Levine, the junior metallurgist who had first noticed her seams, stayed in the defense industry after the war. In 1979, while reviewing archival blueprints for a historical project, he came across a familiar note scribbled in pencil on an old schematic. Variant 3, reed pattern holds under stress. See Hull 1612. He froze. It had been more than 30 years. But he remembered. He spent 2 weeks digging through storage files, tracing the production batch, comparing it with test reports, and finally locating the personnel file for welding shift number 17, Bay 6. Margaret Reed. He wrote her a letter. She did not respond. To field-induced stress dispersion techniques. Those techniques looked a lot like what Margaret had done by instinct. Training centers introduced modules encouraging welders to consider the function of their seams, not just their appearance. What started as a fluke had become a philosophy. In the Korean War and later in Vietnam, armored vehicles bore traces of the same uneven contour welds. Not everywhere, but in the right places, where tension needed to flex, where joints had to absorb shock. The legacy was there, buried in the steel. Meanwhile, civilian industries took notice. In shipbuilding, in oil rigs, in heavy construction. Engineers began to recognize that the obsession with visual perfection often ignored the deeper question: would it hold? By the 1960s, welding schools in places like Milwaukee, Pittsburgh, and Houston began using simulation rigs to demonstrate stress failure paths. Some instructors even referenced a legendary wartime welder whose seams defied expectations, though no one knew her name. But perhaps the most poignant proof of Margaret's legacy came not in steel, but in silence. At tank museums across the United States, restoration crews began to notice something when working on Sherman hulls. A few of the tanks, usually mid-war models from Detroit, had a distinctive ripple pattern along the lower hull and turret seams. Those seams were tougher to grind out. They resisted corrosion better. They looked crude, but they held like concrete. Some restorers began referring to them informally as combat welds. One team at a museum in Pennsylvania even engraved a small plaque inside the hull of one restored Sherman. Welded by hands unknown, strengthened by pressure, tested by fire, still holding. In the 21st century, a group of high school students visiting that tank asked a volunteer why the welds looked so rough. He smiled and said, "Because someone was in a hurry to save the world." The kids laughed. Then they touched the steel. Not many people know this story. It is not in textbooks. It is not in official military doctrine. You will not find it on the History Channel. But if you ever meet a welder who trained in an old-school American shop, ask them what they think about pretty seams. You might hear something like this. "Pretty's fine. But if it's got a hold under hellfire, give me ugly and deep every time." And whether they know it or not, that's Margaret Reed speaking. Through them, through the welds, through every inch of steel that still stands because someone once refused to follow the rules and chose to follow the heat instead. Victory is often measured in battles won, flags raised, or cities liberated. But the truth is, wars are not won by moments of glory. They are won by inches, by seams that do not crack, bolts that do not shear, and people who keep showing up when no one is watching. Margaret Reed was never interviewed. She was never featured in a newspaper. She lived and died in quiet dignity, believing that her job had been just a job. But history tells a different story, because sometimes greatness is not loud. Sometimes it hums like a welding torch in a Michigan factory at 2 in the morning. Sometimes it looks like a weld line so rough and out of spec that even the foreman winces. And yet, it holds. There is something uniquely American about this kind of story. Not the sanitized kind found in museums, but the real kind, where hard work beats high theory, where blue-collar brilliance outperforms the rule book, and where something flawed, something unpolished, turns out to be the strongest thing on the battlefield. It is a reminder that perfection is not always the answer, that sometimes the world is saved by what was almost thrown away. One Sherman tank, 3 direct hits, 0 casualties, and 1 weld that never broke. Margaret never knew what her hands had done, but we do. And that knowledge, that small truth hiding in the steel, is enough to change how we look at history. So the next time you see a tank in a museum, or a welder's spark flashing behind a curtain, or a seam that looks a little rough but refuses to give way, think of her. And remember, sometimes the imperfect hand makes the perfect miracle. What shocked you most? That a bad weld could save a tank? Or that history almost forgot the woman behind it? Tell us in the comments. And if you believe ordinary hands can do extraordinary things, share this story. Let someone else remember her too.